this lecture, which is titled Exploiting Instruction Level Parallelism, here we shall be discussing something like this. You see, in our last lecture, if you recall, we talked about the multicycle operations. So, one thing we saw, multicycle operations instructions, they occupy more number of clock cycles in the EX stage, and if there are data dependencies, then even with data forwarding, significant number of stall cycles are required. So, we cannot do anything about that. If there are instructions like that, that many stall cycles will be required. Say for the integer operations, earlier we saw that in the worst case only one stall cycle was required, but here there can be several. So, we can again look towards the compiler and give the compiler much more responsibility to try and fill up so many delay slots which are there. So, now the compiler has to work much harder, because now we have so many delay slots, and there are many interesting techniques that the compiler use. There is something called instruction level parallelism. Well, unless there is parallelism, you cannot move things around that freely. So, compiler tries to expose more parallelism and then utilize that to reduce the number of stalls. So, we shall try to illustrate this with some illustrative examples in this lecture today. So, let us see. So, our objective is to keep the pipeline full, to reduce the number of stall cycles as much as possible. So, for that purpose, we will have to exploit parallelism among instructions. So, what do you really mean by parallelism? You see, if there is no parallelism, which means instructions are executed in sequence in a particular order. Second instruction depends on the first instruction, third instruction depends on the second instruction, fourth depends on the third instruction. There is no parallelism. But if the instructions are independent, then we can run them parallelly. Parallelly means even we can exchange their order. Two instructions, I can bring one of them before, other later. So, without any problem. So, whenever I can expose more parallelism, I can do two things. One is I can move instruction around much more freely, and secondly, if I have multiple functional units available, like I have a multiplier and an adder, 2 units available, then I can try to execute an addition instruction and a multiply instruction together, such that there is some kind of parallelism among the functional units that can be exploited. Okay? Fine. So, here as I said, when you talk about parallelism, it means sequence of unrelated instructions that can be overlapped, and if there are unrelated, obviously there will not be any data hazards, there will not be any problem. But if the instructions are related, means the output of one instruction is used as the input by the another instruction, then they have to be separated by an appropriate number of clock cycles, that means the latency, that is the latency that depends on the type of the operations. Now, this table summarizes the typical latency figures between the broad kinds of arithmetic operations, particularly floating point we are concentrating on. So, when there are two floating point ALU operations, the latency is 3, this we are assuming. So, the instruction producing results and the destination is a store, then the latency is 2, load followed by an ALU operation 1, load followed by store, there is no latency because the mem stages occur in sequence, no problem. So, these are the figures we shall be using to work out an example. Well, now in the real case for addition, multiplication, division, it can be different. So, the exact values may differ, but we shall be using these figures to work out some examples. Okay. Fine. Now, in addition, we had seen earlier branches will have one clock cycle delay. We are not talking about the predictive methods, the hardware prediction, other things. Simple branch using branch delay slot will incur one cycle delay. And the other assumption that we make, as we discussed in our last lecture, that the functional units like your adder, multiplier, they are fully pipelined except the division unit, and because they are pipelined, you can initiate an operation like addition, subtraction, multiplication on every clock cycle. So, the alternate philosophy could have been to have multiple functional units, means instead of pipelining, let us say the adder unit which consists of 4 stages, we could have used 4 adders, but that unnecessarily would increase the cost 4 times. So, pipelining is a much more elegant method where cost is not increasing that much, but we are effectively we are getting 4 times throughput approximately. Okay. Fine. So, we look at a compiler technique now where some additional parallelism can be created. So, what I am telling is that suppose I have written a program or someone has written a program. So, just by seeing the program, some parallelism can be identified. The compiler will say that, well, that is fine, but let me try to generate some more parallelism. Compiler is doing something more, is applying some tricks there, okay, that we will see. So, if it is done, then the pipeline stall cycles can be reduced quite significantly. Let us take an example like this with which we will be illustrating the process. So, we assume that there is a vector, that means an array of size 1000, S is a scalar number, you are adding S to all the elements of the array. Okay, this is a C code, and we are assuming the register values like this. Let us say R1 points to the last element of the array, F2 register pair contains the scalar S, and R2 is pointing to the element which is just before the first element of the array. That means, if I add 8 with R2, that is pointing to x0. Okay. So, actually R2 is pointing to one element before x0. Okay. This is how we will be initializing R1, F2, R2 such that my code can become like this. For this loop, the corresponding MIPS32 code is this, assuming that R1, F2, R2 are loaded like this. So, what do we do? Let us see. We are loading 0 R1, R1 is pointing to x1000, that means the first number, into F0, F0 F1, add double F0 with F2, F2 contains the scalar, result is in F4, we are storing F4 back into 0 R1, so result back into Xi. You see, this R1 is pointing to the last element, right, and in double precision, so every element is 64 bits, that means 8 bytes. So, after one after one addition, we are decreasing R1 by 8. So, we can either do add immediate minus 8 or subtract immediate 8, both are okay. So, here I have given add immediate R1 minus 8 store in R1. So, now it will be pointing to x999, and we repeat until R1 becomes equal to R2. R2 is pointing to the element just before x0. So, when it decreases and crosses x0, you stop, or otherwise you go on looping. Okay. Let us analyze this code first. You see, there is a load followed by an add. So, according to our earlier table, a load followed by its use will incur one stall. An add, you are storing in F4 and storing this F4 you are storing. So, add followed by a store will incur 2 stalls. You see that table, just from the table I am showing. So, here there is no dependency, and one thing we mentioned that for branch there will be 1 stall cycle as usual. So, for every branch there will be 1 stall. So, you see that for the program for this loop which consists of 5 instructions, for every loop it will actually require 9 clock cycles, 9 clock cycles per iteration with 4 stalls. Okay. This is what this code gives. Let us now, okay, so this was our code. This was our code. So, let us now try to do that instruction scheduling that we learnt earlier. So, let us keep the same code, let us try to move some instructions here and there and try to reduce the stalls. So, this was our original code. Let us do instruction scheduling like this. The first thing is that this add immediate instruction, this we are moving earlier, we are moving it here such that between load and add the stall disappears. So, we have moved this add immediate here, and because we have decremented this R1 earlier. So, earlier this store was 0 R1. So, now this store becomes 8 R1 because already you have decremented, right. So, this 0 is changed to 8. Then we have the add followed by store and BNE. This was the modified thing. Another thing we do, this is shown here, the store is moved to after BNE to fill up the branch delay slot. This also we can do because the store and branch are independent, okay. And whenever this branch is done, the store will also happen along with that. So, if we do that, then you see for this loop there will be 7 cycles per iteration, there are 2 stalls. So, you see, so our program had 1000 iterations. In the first version there were 9 clock cycles per iterations, which means there were total of 9000 clock cycles required. But now in this version we are having 7 clock cycles per iteration. So, from 9000 we have brought it down to 7000. Okay. But you see, with this code, however hard the compiler tries, it cannot improve any further, right. So, what is the way out? The way out is to do something called loop unrolling. Let us try to explain what it is. You see, this was our original loop. So, means we are going back to the original loop. So, original loop was looping 1000 times. Now, what I am doing, my philosophy is this: there are 1000 elements, I have written a small loop for adding 2 numbers, I am repeating 1000 times. Now, in the modified version what I do, I unroll the loop. This is called unrolling. Unrolling means, see earlier I was only adding xi with s. Now, what I do, I add xi with that means in terms of C program it will be something like this. I write xi equal to xi plus s, then I write xi minus 1 equal to xi minus 1 plus s, then I write xi minus 2 xi minus 2 plus s, I write 3 times, I do 4 times, means I unroll it 3 times to make it 4 copies. So, I unroll it 4 times and I make a loop on this. So, I give the for loop. For you see, earlier it was I was starting with I equal to 1000, same thing, but in the previous case I was going up to 0. So, here I will be doing I equal to I minus 4, I will be plus 4, increasing it by 4 times in every iteration, and here I will be repeating till I greater than equal to 0, same thing. So, the idea is the same. What I do is that instead of the original loop which was repeating 1000 times, now I have a loop which will be repeating 250 times. But in the body of the loop I have 4 copies of addition. I am adding 4 different, these are independent. You see, this is working on xi, this is working on xi minus 1, this is xi minus 2, xi minus 3. There is no data dependency between these blocks, right. This is called loop unrolling. So, here this code I am unrolling, and you see this load, add, store, there are 4 versions of load, add, store. First is with 0 and 0, second one is with minus 8 and minus 8, third one with minus 16, minus 16, fourth one with minus 24 and minus 24. That means the 4 elements. So, once we have done this summation for 4 elements, instead of adding or instead of subtracting 8 from R1, now you are subtracting 32 from R1, and the branch condition remains the same at the end, right. Now, you see even without doing any instruction scheduling, what are the things we have done? See, just to calculate the stall cycles, I am not shown the stalls here. See, number of stalls per loop, actually how many will be there? Load followed by add, there will be 1 here, 1 here, 1 here and 1 here, right. And there will be 2 here, add followed by store, 2 here, 2 here, 2 here and 2 here. So, there will be 3 stalls every for this 4 times and 1 for the branch. So, 12 and 1 13. So, total there are 14 instructions you count, there are 14 instruction plus 13 stalls, 27. So, in this version of the program, cycles per iteration will be 27 by 4 equal to 6.8. Okay. Now, you see we have exposed so much parallelism. Now, we can move instructions around much more freely, right. This was the version that I showed last. So, now let us move instructions around. Just a second, this was the thing, this was the code. So, this same code I am taking. So, I am moving around. What I have done, all the load instructions I pushed together, load, 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 load. So, all the 4 adds I pushed together, add, 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 add. There are 4 stores, store, store, store was 3, and the 4th one I put in the branch delay slot, and I have adjusted the numbers according 0, minus 8, minus 24, this is okay, and these are all right. Only for the last store, because they have already subtracted minus 32, it was minus 24, right, but I have already subtracted minus 32. So, this has to be plus 8. Minus 24, minus 32 plus 8 is minus 24. So, you see in this version there are no stalls, because there are no dependencies like that, they are all independent. So, whenever you have this add, this is so far apart, there are 3 instructions in between. Similarly, between add and store there are 3 instructions in between. So, no need for any additional stall cycles. So, there are 14 instructions, 14 clock cycles. So, 14 by 4. So, there are 4 computations you are doing per loop, 3.5 cycles per iteration. So, if you just compare, in the earlier version for computing 1000 numbers, you were doing effectively 9000 cycles, 9 clocks per iteration. From there, after instruction scheduling, you went to 7 cycles per instruction, that means 7000 cycles. But here 14 by 4, why? because we are computing adding 4 numbers in this loop. So, for every iteration 14 by 4 3.5. So, here you are bringing it down to 3500. So, you see there is a quite drastic reduction in the number of clock cycles. So, here if the compiler does this instruction scheduling, it can bring down the clock cycle to a great extent, right. Fine. So, to summarize loop unrolling can expose more parallelism obviously in instructions. It can be used to lower the cycles per instructions in architectures. This we shall be talking about now, where more than instructions can be issued per cycle. You see, normally in the machines we have seen so far, the pipeline, we said that our ideal CPI cycles per instruction was 1, but now we are talking about machines where the CPI value can be less than 1. Cycles per instruction is less than 1. What does that mean? We are using some kind of parallelism. Let us say 2 instructions are executing together. So, in every cycle you are executing 2 instructions. So, my CPI will be 0.5, okay? Something like that. Okay? We are trying to reduce CPI to a value less than 1. So, broadly there are 2 kinds of approaches. We will be very briefly talking about this. One is called superscalar architecture, other is called very long instruction word or VLIW architecture. So, first we look at a superscalar version of a MIPS32. First we see what is a superscalar machine. Superscalar machine means actually it is a computer system, it is a processor which can issue multiple instructions in every clock cycle. That means the idea is that very simple. We have seen a pipeline for MIPS32, right. Now, you imagine a superscalar version of MIPS where there are 2 pipelines, not 1. I have replicated the pipeline. There are 2 pipelines. So, in every clock cycle I will be fetching 2 instructions, I will be feeding the 2 instructions in the 2 pipelines. So, in every clock I will be feeding 2 instructions to the pipeline. So, in general the number of such pipelines can be more than 2, it can be 4, even higher. This is what is meant by superscalar. Okay. So, machines can issue multiple independent instructions. Obviously, this has to be independent. If there is a dependency between the instructions, you cannot start them together. Okay. So, the hardware issues a fixed number of instructions 2 to 4. The hardware can also check for conflicts whether they can start together. If there is a conflict, then only one of the instruction can be issued and the others have to wait. Okay. So, a superscalar architecture schematically looks like this. So, now our fetch unit will be more sophisticated. So, from the cache memory it will have to fetch more than 1 instructions every cycle. Decode and issue units will also be decoding several instructions together, and there will be multiple pipelines. I am calling them as functional units. You can imagine that as if they are independent pipelines. They are all accessing maybe a common register file. So, depending on the capability of the machine, suppose there are 4 such. So, 4 instructions will be fetched together, they will be issued, 4 concurrent instructions can be issued to the 4 pipelines. So, the conceptual it is like this, the instructions are stored sequentially, they are fetched much faster, and let us say 4 of them are fetched and 4 of them are fed to the 4 pipelines. This is the concept of superscalar architecture, right. So, just an example for a superscalar architecture with 2 functional units. Let us say there are 2 functional units, one of them can be a functional unit which can handle load, store, branch and integer operations, and the other functional unit can handle floating point operations. So, in every clock cycle you can start 2 instructions, one integer, one floating point. Okay. Actually, here we are not showing multi-cycle operations, because in general for floating point there will be multi-cycle. Just for the sake of illustration we are showing this. Similarly, in the next cycle there will be one integer, one floating point, next cycle again one integer, one floating point, like this. So, the idea is something like this. So, dependency between instructions will be checked dynamically in the hardware, this is important. Now as an alternative, well, again we can give some responsibility to the compiler, but that is not for superscalar architecture, for the other kind of architecture, VLAW. So, what the compiler can do, see, for superscalar what I am saying is that instructions are fetched, the hardware is dynamically checking whether there are any conflicts. If no conflict, they are fed to the pipeline together. But now I am saying there is another kind of architecture we are proposing, VLIW, very large instruction word, where the compiler is trying to create packets of instructions, like each packet will consist of 4 instructions, and the compiler will ensure that 4 instructions are such that there is no conflict between them. So, hardware need not check for anything, they will simply take a packet and issue to the 4 functional units, just like that. Okay. So, this is the idea. Now, there are some issues, like for example, if we issue an integer and floating point operation in parallel, because they use different register sets, different functional units. So, additional hardware required is less, okay, because they do not normally share register sets. The only conflict is when the instruction that is handled in the integer unit is a floating point load, where the loaded value has to be stored into a floating point register. So, that can lead to a hazard. Okay. So, another issue is that for the original MIPS pipeline, whenever there is a load instruction, latency was 1, but for the superscalar version it is not 1, it will be 3, because not only the next instruction that is coming together, but in the next clock the next 2 instruction also has to wait, because of that latency of 1 cycle. So, now latency in terms of the instruction will be 3. So, 3 instructions will have to wait rather than 1. Similarly, branch delay will also become 3 cycles and not 1. Now, VLAW, as I said, so the instruction word is made much wider, means an instruction word can store several instructions together. Okay. Several instructions together is referred to as a macro instruction, maybe 2 or 4 like that. Okay. So, there are similarly several functional units, the compiler will be generating these macro instructions, we will be trying to group the instruction together. The responsibility to identifying the set of instructions that can run concurrently lies with the compiler. So, you see the architecture wise, here it looks similar, but it takes a packet, of instruction. So, now instructions are coming as packet, not one by one. So, an entire packet comes where the instructions in a packet are guaranteed to be independent, the compiler has ensured that. So, fetch will directly feed here, right. So, the idea is something like this. So, let us take a small example. Let us take that unrolled program that we showed earlier for that vector scalar sum. Let us see how we can run it on a VLAW processor and schedule it, where we assume that the VLAW processor has 4 functional units, where 2 of the functional units are memory reference units which can handle load and store. There is 1 floating point and 1 integer operation which can handle also branch. So, you see, for load and store there are several instructions, for floating point there are these add instructions, and for integer operation there is only this branch and this add immediate, right. Let us see how it can be scheduled. So, here I am showing one possible schedule, you can check this. These are the two load function units, load store, this is the floating point function unit, this is the integer function unit. So, the loads can be placed together in the first two cycles. So, after the loading is done, the floating point ALU, so you can put the adds here. The stores, there will be a delay of 2 cycles, you can just after this F4 is there, after a gap of 2 cycles you can start the store, and this branch again of course. So, like this. So, here you see there are 1, 2, 3, 4, 5, 6, 7, 8, there are 8 cycles. So, for 4 instructions you need 8 cycles. So, the cycles per instruction becomes 2.0 because of the parallelism which is supported. There are physically 4 parallel hardware units. Okay. So, for processing 1000 numbers, number of clocks will become 2000. Okay. So, with this we come to the end of this lecture. Here we have looked at some of the ways of parallelizing or speeding up the basic MIPS32 processor, which contains not only integer units, but also floating point units. Now, this superscalar or VLAW are quite very standard architectures available nowadays. Many of the processors that you see around us, they are actually based on superscalar architectures. Now, one thing I have not mentioned here, this is actually beyond the scope of this class, this course. You see, when you have this multiple issue kind of a thing, superscalar architecture, there are so many instructions coming, you are dynamically decoding them, dynamically detecting the presence of hazards. You need something called a scoreboard, that is a hardware based data structure that will be maintained by the control unit dynamically, and it will immediately tell you whether there are any scope for any hazards, whether you need to insert any stall cycles and not. Okay. So, these we are not discussing in this class. Thank you.